Welcome back, everybody. So in the last video we were talking about mass balances, and yeah, mass balances. What about mass balances? We have derived for ourselves this expression here for a microscopic or differential mass balance. So we have subdivided our problem into many small cubes, and this is the equation of mass balance for each of those cubes, those smaller cubes. And that's the general principle with differential analysis. We look at a small cube or a small block of the whole problem, and then we have equations describing what's going on. So this is mass balance, all right? And this is step one, just before we actually start the Navier Stokes equations. And if you actually see the textbook properly, the Navier Stokes equations are describing momentum, which is Newton's second law. Momentum balance. Now these are what Navier Stokes are actually about. Okay. So we have to perform that over the same box that we were talking about earlier. Now in a textbook, you'll probably see that the Navier Stokes equation only refers to this momentum balance, but I kind of like to lump these two together. Well, it's easier to remember that way, because you don't have momentum balance without mass balance. So if you want to describe a fluid, you need this Navier Stokes equations. And in fact, if you look at the Navier Stokes equations, you actually combine both the mass and momentum balances together in order to simplify the equation. So the mass balance is inside there somewhere. It's just not that explicit. Now, anyway, the thing is that about the Navier Stokes equation is that it's going to get really complicated with many terms. So the emphasis is on many because I'm repeating that word a lot. So since we have many terms, we want to learn a few. We want to learn a few ways to truncate equations. So now this equation is relatively, it's compared to the Navier Stokes equation, it's going to be relatively simple. But it already looks a bit scary. And imagine a Navier Stokes equation is going to have 12, it could have up to 12 terms. It is that number, or easily more than 10 terms in each equation, and you have 3 of those equations. Because for momentum balance, we have an x, y, and z direction, or depending on the coordinate system you use, you have a r theta phi or r theta z. If you're talking about cylindrical or spherical coordinates, we can deal with that later. Point that you want to take home is you want to truncate these equations. So how are we going to truncate these equations? Well, let's introduce some operators. Let's introduce some operators. Well, first of all, I want to call this the gradient. Okay, the gradient operator. And what is it? Okay, it will be like this. So I just okay. How do I type this out? I use a bracket, space bar. I'll go inside using the arrow keys, and I press enter 2 times. Okay, so the gradient operator is basically a partial y partial x, partial by partial y, and a partial by partial z. Now, that's all that the gradient is doing. Now, if you have a divergence operator, it's very similar to the gradient. Okay, divergence, nabla or del dot. So the dot is usually this. Alright, so you have this gradient operator here, and then you have a dot. You should know some of this before, but I'll kind of explain what this is actually doing in a bit. So, hopefully you have learned about vectors a while. If not, please do go and watch a video about vectors. Alright. Yeah, do go and watch a video about vectors to get introduction to these. I don't want to spend too long covering, basic concepts. Okay. So how can we use this divergence to simplify this equation? Well, you see this dot product, right? If you see a dot product, it means that it takes two vectors and it makes it into a scalar. So what I'm highlighting now, this is a scalar. This is a vector. So this scalar can be represented as the dot product of two vectors. One is this divergence, this del x, del y, del z. And you can see the del x, del y, and del z already. So all we need to do is make another vector representing the velocity multiplied by this density. So what's in the del by del x? That will be rho u. What's in the del by del y? It will be rho v. And del by del z? Rho w. Right? So we have this, and we just compress it into a vector form. You can see the dot product is this times this plus this times this plus this times this. That's all we are doing here. So that's sort of what we end up with. Okay, so the correct way of writing this is you have all these densities that are here, these are talking about the same density, sort of the same density. Okay, so I'm gonna have a velocity vector, right? So if I want to simplify this, it'll be like this. Okay, so we have compressed these three terms into something like this. It's a very compact way of representing all of these. So I've just introduced you the gradient operator and the divergence operator. So what this does is to help us truncate some of these equations to make it shorter, so that when we do our Navier Stokes equations, it will be something a little more manageable. So where do we go with this? Now we can just factorize out this this gradient, this density here. Okay, so we have this. Let's factorize out the density. Blah blah bullet rho bullet. Let's use v or u. So this v, which I use the vector notation, v vec equals to u. Okay, then I need to have a v and a w. Okay, so now I've used the vector notation to make this thing even shorter. So you see, we have three slightly messy terms and we got to spend lots of time writing, but we can just use this notation here when we factorize the density out to arrive at this. This very simple, very compact way of writing this partial by partial x, partial by partial y, partial by partial z. Okay, and that will give us the equation, the same mass balance equation. We can just compact everything. Rho v vector. There you go. This is mass balance. Okay, this is just the mass balance, which I'm writing another way. So while we're writing this, we want to keep our equations very simple and don't spend so much time writing. And if you want to memorize things, this is way easier to memorize than this. Yep. So you memorize two terms rather than this, and as long as you know what this divergence means, you're pretty safe. Alright, so let's start with our momentum balance. So what is momentum balance? This is basically Newton's second law performed around our quote-unquote box. So let's draw a box again. Okay. 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 A very poorly drawn box. Okay. Okay, we have our box again. A rather poorly, shoddily drawn box. Okay, so we'll have momentum balance. What does the momentum balance or Newton's second law say? Alright. Okay, the Newton's second law says that if you are doing in SI units anyway, the force, net force on the body, equals to or is proportional to rate of change of momentum. Right? This is all Newton's second law is saying. Alright, so we want to find two parts. One is this net force on the body, and the other part is the momentum change within this box. Of course, this box is actually staying still. However, there are flows going in and out. Alright? So we'll need to take note of that when we consider the change of momentum. So let's write this down in equation form, or at least write down something. Net force on a body equals to rate of change of momentum, if you're talking about SI units anyway. So we are going to derive in SI units, so it is just equal, the constant of proportionality is 1. Okay, so the net force on the body. What are the forces acting on this little box here? Well, these forces can come in two forms. Firstly, we can talk about stresses. And secondly, we can talk about body forces. Now, what are stresses and what are body forces? Alright, if you're talking about stresses, maybe you look at this box and then you see this face here. You see this face here, this front face, and then you decide to apply a force this way, a large force this way. Now, this is known as a stress. So this is parallel to this this plane here. You are applying a stress parallel to this plane, and if the stress is parallel to this plane, it is known as a shear stress. So stress is merely like force per unit area, but instead of it's in a vector form rather than a scalar, because pressure is a scalar, stress is a vector. So both are in force per unit area, but the stress has direction, just like force. Alright, so if you're wanting to find out the force, alright, we're wanting to find out the force applied by this stress. This stress, we'll call it tau, because tau is usually what we use to denote the force acting on this side. This tau equals to the force over area. Alright, and what we need to do to find the force of this exerted by the stress, we'll need to find the area, and well, we'll draw a coordinate system again. We have the x direction, the y direction, and the z direction. So x, y, and the z. Okay, so we'll have a dx here. Okay, so dx, or delta x as we like to start, delta x, this is delta y, and this is delta z. Okay, hope you don't mind the handwriting. Alright, so we have tau forces, which are the shear stress. We can also have shear stress in this direction, and we can have shear stress in the z direction, this way. Okay, so alright, so what do we have here? We have the stress in the x direction, the y direction, and the z direction. Of course, in reality, you can have a stress in any random direction, but of course, you can decompose this vector into this x direction, y direction, and z direction. That's all we have to do. Now, I know this green is going to be very confusing if I use too much of the same color. It's going to be a point that you can't see much. So I'm going to get it back to the box. I'm going to write, label it properly, delta x, delta y, and the last part here, delta z. And I'm going to push it here. Alright, so these are the stress forces I'm talking about, and each phase can have a stress force that's acting on it. And now, of course, with the 3D problem, you have 3 directions of those stresses. So you can see this problem is going to get really complicated really quickly. But don't worry, we'll take it one step at a time. So each phase will have a force acting on it that you can decompose into 3 vectors. And you can call it in the form of stresses, which are in the x, y, and z direction. Now, that's just the concept before we go into the others. Now, what about body forces? Body forces are things like gravity. And, well, gravity doesn't really act on a face of the box. It acts within the box, so to speak. It's acting on each molecule of fluid or each element of fluid within the box. And then we'll have to consider that as well. We need to consider gravity, or in the case of a ferrofluid, if the fluid happens to be magnetic, then we'll need to consider magnetic forces as well. These can come in the form of, if you have iron powder mixed with oil, you have a ferrofluid, or if you have a sort of a plasma. If you do plasma physics, you'll have to consider magnetic fields as well. If you're doing like nuclear fusion studies or something like that, you have to consider the magnetic field that is keeping all this plasma in the control. So that's because a plasma is a fluid as well. It conducts electricity, and therefore it can be also affected by a magnetic field. Okay, so these are the body forces. But for now, we don't consider magnetism, we'll just consider gravity. And the rate of change of momentum, well, let's talk about that maybe later. Okay, so I'll try not to keep this video too long. Let's talk about the stresses first. Okay. Now with the vectors, as always, it's always a little troubling, because which side are we going to define as positive? So we have an x, y, and z direction. So I'm going to draw these arrows here. Okay, as always, x, y, and z direction. So we got our x, y, and z directions. Yeah, and we want to find out which direction is positive, because for vectors we need to define what is a positive direction. And it turns out for stresses it's slightly more complicated than let's say a force. A force, you can just describe one direction. Let's say you want your x direction is this way. For a force, you can just define this way as positive. So this arrow here will define the positive. So if it goes in this direction, the positive x direction, we can define a force as positive. With stresses, it's not so simple. Okay, so let's break it down first. We're going to talk about vector conventions. Okay, some vector convention for stresses. Now this is going to take quite a while, so we'll put a stop to this video, and we are going to carry on this analysis in our next video. Thank you, and see you next time.